Have you seen something that looks like this? You see, a long time back, I missed a couple of my lectures, and when I went back to class, the professor was doing calculations with symbols that looked like this. I couldn't understand anything. It took me some time to figure out the mathematics of it, and probably a longer amount of time to figure out what actually Kets are, or bras, or Hilbert spaces, or inner products are. So I'm making this video for that past me in an attempt to give a more intuitive explanation of what these concepts are in quantum mechanics, or rather in the matrix formalism of quantum mechanics. So hi, welcome back everyone. First of all, a very happy new year 2025, and let us start this new year with the very first lecture on advanced quantum mechanics, where I'm going to talk about all these concepts and I'm going to introduce the matrix formalism of quantum mechanics. So the very first video on Dirac notation. So first of all, what is a ket? You see, till now, in all our earlier lectures, the entire playlist of 40 lectures of Introduction to Quantum Mechanics, we have more or less discussed this topic or this concept called the wave function. We have solved the wave function for various potentials, and we have talked extensively about the information stored in these wave functions. You see, in quantum mechanics, the wave function is not a physical quantity. It is a mathematical function that contains some information about the quantum mechanical system, which when we perform certain kinds of mathematical operations, reveals to us some important information about the quantum mechanical system. For example, the position probability density of a particle in a quantum mechanical system, the average of the energies of that particular system, etc., etc. Now, the wave function is a mathematical function. For example, if I take the very common example of an infinite potential well, which most of you are familiar with, then you are familiar with the eigenfunction solutions of an infinite potential well. Yes, they are written in a very simple fashion. Psi n is root 2 upon L sine n pi x upon L. These are the eigenfunction solutions of an infinite potential well. And there are infinite such eigenfunction solutions, every solution corresponding to some discrete energy level. And the general wave function for that particular system at time t is equal to 0 is written as a linear superposition or summation of these eigenfunction solutions. What is important to notice here is that these wave functions are mathematical functions of x, or position, right? Now, this is what we call as the quantum state in position representation, or the quantum state of an infinite potential well in position basis. Now, we have also talked in one of my earlier lectures on momentum space representation. So for the same potential, we can also write the quantum state in terms of, let's suppose, the momenta of the particle, which sometimes is written as phi p. All right. So what I want to say here is that all this time, the wave functions or the eigenfunctions that we have been dealing with, they are written as mathematical functions either in position space or in momentum space. So how is all that related to this? Well, this is nothing but the quantum state, but independent of either a position representation or a momentum representation. It is free of any kind of a specific representation that we are usually dealing with. Now, whenever we are dealing with wave mechanics or Schrodinger's wave formulation, most of the time we are dealing with the wave function solutions, right? But now we are going to enter into a little bit of an advanced sort of a formalism of quantum mechanics, where we will represent the quantum states not necessarily in this manner, but in a more general, more abstract quantity or entity known as Kets. These Kets are, quite simply put, the quantum state. That's it. We know that all quantum mechanical systems have some state associated with it, and the state has some information about that system. And when we perform certain calculations, they act like magic and they give us some information about the physical system. So this Ket is nothing but the quantum state, but free of any kind of a representation. What do I mean by that? To understand that, I will give you an analogy from geometrical vector analysis. Okay, so you guys are all familiar with how do we represent vectors. Okay, in space. So whenever we are interested in representing vectors, and this is what we usually study in high school, that we have a coordinate system, usually x, y, z, and then vector is drawn as an arrow from one point to another, and that arrow has projections on the x-axis, y-axis and z-axis, and using those projections the vector is very commonly written as ax, let's suppose x cap, plus ay y cap, plus az z cap, where ax, ay, az, these are nothing but the projections of this vector onto the xy axis. And this is perfectly fine. We have been dealing with these kinds of vector notation since forever, right? But if I make a change to the coordinate system, if instead of an xyz Cartesian system, I take polar coordinates, I take spherical coordinates. So now suddenly the representation of this vector will change, because the moment I take polar coordinates, we are not interested in the projection of the vector into xyz axes, but we are rather interested in the radial distance, in the angular displacements, in the azimuthal displacement, etc., etc. So now with respect to the spherical coordinate system, the same vector might have components, let's suppose ar, r cap, plus a theta, theta cap, plus a phi, phi cap. I think most of you are familiar with this kind of a thing, that the vectors themselves remain the same. There is no change in the vectors themselves, but the way we write the vectors in terms of the components, the numbers associated with the vector, they change depending upon the coordinate system. Even if I translate the coordinate system or I rotate the coordinate system, all these numbers are going to change. So essentially, when I represent a vector either in this manner, or some of you who have studied linear algebra might have seen that a more popular way of representing a vector is just by using the components as elements in a column matrix. This is very much dependent on the coordinate system that we are using. Now the question is, what has all these things got to do with the Kets? You see, what I'm trying to make you understand is that when we write down vectors in Euclidean geometrical space, the representation of the vector is very much dependent on the coordinate system that we are using. We rotate the coordinate system, we translate the coordinate system, we take a different coordinate system, spherical coordinates, cylindrical coordinates. These numbers are going to change, but the vector itself doesn't change. The information about the magnitude and the direction of the vector itself doesn't change, even though these numbers can change. So that's what I'm trying to tell you, that when we talk about quantum vectors or quantum states, we try to represent them by something that is more general, that contains the information about the quantum mechanical system, but is independent of the nature of its representation. For example, if I represent the quantum state in position basis, we end up getting this nature of a wave function solution. If I represent the state in momentum basis, I may get a momentum space representation. But there are different ways of representing a quantum mechanical system. So for example, later on, when we will be discussing the harmonic oscillator, we might be referring to the states of the harmonic oscillator by something like this, like a n. Or if we study spin angular momentum, you might see that we represent the spin up of an electron using a column vector 1, 0. See, the whole point of a ket is that it is some quantity that contains information about the quantum mechanical system, information about its energy, its position, its momentum, its spin, etc., etc. And it can only reveal to us that information through various kinds of mathematical calculations, mathematical operations. But the way we represent them, those quantum states, does not have to just be in the form of these kinds of position wave function solutions. And this kind of a representation was first introduced by Dirac, and therefore we call it the Dirac notation, which includes Kets and bras, etc., etc. And this notation of representing the states as Kets and bras and everything else that is going to follow is very much an integral part of learning modern quantum physics. So, what is a ket? Well, ket is simply the quantum state or state vector, whatever you want to call it. It is the quantum mechanical state of the system which contains all the information, or you can call it just state, or you can call it state vector. Now the question is, why do we call it a vector? Because this is not the same vector as this. Because these kinds of vectors, which also we deal with in physics, mostly in mechanics, like position vector, acceleration vector, force vector, etc., etc., these vectors only exist in three-dimensional space. On the other hand, in quantum mechanics, the state vector is something that exists in what is called Hilbert space. Now, I will make a detailed video on what Hilbert spaces are, but quite simply put, Hilbert spaces is the mathematical abstract space to which these kinds of quantum states belong. So, Kets live in Hilbert spaces, just like monkeys live in trees, dolphins live in the ocean, snow leopards live in the mountains. Kets live in Hilbert spaces. Does that make sense? Okay, let me try one more time with a little bit of a different example. If I take a number, any random number, it belongs to a mathematical space called a real number line. But instead, if I take a complex number, it belongs to another mathematical space of complex numbers. If I take, for example, a geometrical vector, it belongs to Euclidean space. If I take various mathematical functions, it also belongs to function space. Similarly, Kets belong to Hilbert spaces. That is all I'll explain right now. I'll make another video on Hilbert spaces later on, because these are not the criteria of Hilbert spaces. There are a lot of criteria for a linear vector space to be a Hilbert space. But I just want to give you the introduction that these are mathematically abstract collections of Kets that contain information about the quantum mechanical system. Now, to every ket, there belongs something called a bra. Now, why do we have these names, bra and ket? I'll come to that in a moment. The bra is essentially written in this particular manner. To every ket, there is a bra, and to every bra, there is a ket. Now, you might ask, what is the relationship between them? Well, for example, when we were discussing wave mechanics, we always used to talk about wave functions and their complex conjugates. So, if I have a wave function psi, we would easily be able to obtain the complex conjugate of the wave function. And the complex conjugate is important because wave functions themselves are complex mathematical functions, and whenever we want to find out, let's suppose, the probability density of a particle, we would multiply the wave function with the complex conjugate and integrate it over the region in which we are trying to find the probability. So therefore, in a similar manner, in a more generalized approach, the ket has the corresponding bra, where the corresponding bra elements consists of the complex conjugates, although that's just the simplistic version of it. But just like wave functions have complex conjugates, kets have bras. Now coming to the most important point, what can we do with them? Well, there is something called inner product. You see, till now, whenever we have been able to solve a Schrodinger equation to obtain a wave function for a system, the first thing we do is we find out the probability density of that quantum mechanical system, right? The first thing that we do is we take the wave function, we multiply that with the complex conjugate, we integrate it over that region, whether it's in the 1D axis or in the 3-dimensional space, and that helps us figure out what is called the probability density of the particle. What this represents in the context of our abstract Kets and bras is essentially called the scalar product or the inner product of psi with itself. Now, if you look at this product, which is the inner product, this looks like a bracket, isn't it? This looks like a bracket. And from this word bracket comes the word bra and ket. Do you see what's happening? This essentially comes from the word bracket. So essentially, when we deal with bras and kets, we are mostly interested in figuring out their inner products, because their inner products give us an idea about something that's happening in the quantum mechanical system. So for example, if I take two distinct kets, let's suppose I take a distinct ket psi and phi, I can find out the inner product or the scalar product of psi and phi in this manner. This is how it is represented. But the question is, what does it actually mean? Well, first of all, if I try to explain using the analogy of wave functions, this can be written if I have the psi and the phi kets written in terms of the position representation. I end up getting the wave functions associated with psi x and phi x, and that is essentially phi x, psi x dx integration. But what does it even mean physically? For that, let us go back to our example of vectors, because the vectors help us give an analogy of trying to picture what's happening, because we're dealing with abstract concepts here and it is very hard to sort of have any kind of a physical example which could help us understand what's going on. So we're trying to extrapolate, make connections to help us understand what's going on. Imagine you have two vectors, like for example, you have a vector A and another vector B. Okay. Now, if I take a dot product of both the vectors A dot B, what does it mean? It means that A has a set of components with respect to the coordinate system, B has a set of components. We take the summation of the product of their components. So AX, BX plus AY, BY plus AZ, BZ. Okay. Now this basically gives us an idea about the projection of A on B or B on A. Alright, so for example, if I take the shadow of A on B, the dot product gives us the amount of that particular shadow. So the dot product or the scalar product gives us an idea about the similarity between A and B or the commonality between A and B. If I want to write A in terms of B, then the dot product gives me an idea about that. So just like in vectors, we have a dot product that simply gives us an idea about what is the similarity between two distinct vectors. We have the inner product with this abstract ket representation. This inner product, what it essentially means is, if we have two distinct quantum states, phi and psi, what is the similarity between them? Can one state transform into another? And in fact, this inner product represents nothing but a very simple thing in this particular formalism, which is the probability amplitude of a system going from state psi to state phi. So that means if at time t is equal to 0, a quantum mechanical state is phi, then the question is, at a later time, what is the probability amplitude that the system will be in the state phi? And that's it. The probability amplitude of one quantum mechanical state evolving into another quantum mechanical state is what is given by the inner product. That's all. This is essentially the sort of a dot product of these Kets and bras. All right, and if the dot product comes out to be 0, what does that mean? If the dot product comes out to be 0, it simply means that these vectors are perpendicular. Vectors are perpendicular. What is the meaning of perpendicular? It means that one vector cannot be written in terms of the other. One vector cannot be decomposed in terms of the other. The projection of one vector on the other is absolutely 0. And it's the same here. If the scalar product is 0, it simply means that this kind of a transformation will never happen. A state which is in state phi will never evolve into a state psi if this is equal to 0. And in a way, the inner product kind of generalizes this concept of a dot product in geometrical vectors in Euclidean space. Now, this information that we are constantly talking about, that the Ket holds within it about the quantum mechanical system, about the positions, the energies, the momentum, the angular momentum, all these other kinds of physical quantities that the Ket somehow has hidden within it. How is it revealed? It is revealed by a very simple operation, We have in quantum mechanics what are called operators, and I'm just going to mention this in passing, okay? We will talk about them in detail later on. That we have in quantum mechanics what are called operators whose job is to operate onto the Ket. So for example, if I had some kind of an operator, let's suppose A, and we usually represent these operators as with a hat on top, and this operator is acting on a Ket, let's suppose psi or something like that. Now this A could be anything. It could be an operator for energy, it could be an operator for momentum, it could be an operator for position, angular momentum, spin angular momentum, etc. Essentially what happens is that if this is a eigenket, which means that it is a solution of the Schrodinger equation, then you end up getting an eigenvalue equation, which means that you can represent this with a lambda, which is a scalar, and the Ket itself, where the lambda itself is some number or value that corresponds to the physical quantity whose operator is represented by A. For example, if we talk about, let's suppose, energy. So when we talk about energy, we use the Hamiltonian on a particular Ket, which let's say is an eigenket. That means it's a pure state of a system, not a superposition of states. Then we end up getting the energy corresponding to that particular eigenket. So for example, if I represent the eigenkets of the infinite potential well, and if I take psi 1, then I would end up getting E1 psi 1, where E1 would be the ground state energy level corresponding to the first eigenket. The Ket is some quantity that has some hidden talent or information, and the operator is like a director, sort of directing the Ket and trying to reveal something out of it that we can use for correlating with the actual physical quantities in the actual physical system. So for example, if you think of the Ket as like an actor, like let's suppose Leonardo DiCaprio, and the operator as Nolan or something, then you end up getting Inception. But if you replace Nolan with Martin Scorsese, then you end up getting The Wolf of Wall Street. But instead, if you have Christopher Nolan operating on Matthew McConaughey, then you end up getting Interstellar. You're getting what I'm saying? This whole business of the formalism of quantum mechanics is that we represent the quantum states in terms of these Kets, We perform various operations of these Kets, and one of them is when we operate some sort of a mathematical operator onto the Ket that will give us some kind of an information about that physical quantity of that system. So if I operate the same operator but on a different Ket which corresponds to the first excited state, then we end up getting E2 psi 2. Okay, now this E1 and E2, these we can compare with actual physical information about the energy of that particular system. So this is altogether a very interesting sort of a formalism where we deal with these Kets, which are the quantum mechanical states of a given system, but devoid of any kind of a representation in position space or momentum space. Let me give you a couple of properties associated with Kets. Okay, so now that instead of wave function solutions we'll be dealing with Kets, it's important to know that we can add up Kets, So for example, I can add psi Ket to, let's suppose, a phi Ket to get some other kind of a gamma Ket or something like that. So we can add Kets. We can also, because we can add Kets, we can represent the state of general state of a quantum mechanical solution in terms of the eigenkets. So for example, if I want to write down the general state of an infinite potential well, then that is represented by the summation of the eigenkets, which are essentially the pure states, while this is the linear superposition of those pure states. The inner product of one state with another. Now here the ordering is very important. If I want to write down, let's suppose, psi first and phi later on. So here we have psi Ket and phi bra, but here we have psi bra and phi Ket. Then they are not necessarily equal because the inner product always ends up giving you some kind of a scalar. And the scalar here in this context could be a complex number. So when we sort of change the ordering, we have to take the complex conjugate of that. One very important representation of the Ket is in matrix representation. When we represent the Kets using matrices, especially in a discrete basis. If I have a psi Ket, then it could have a column matrix representation, let's suppose A, B, C. On the other hand, the bra of psi would simply be the not just the complex conjugate, but what we say the Hermitian adjoint. So here we would get a row vector with the components involved are the complex conjugates of A, B, and C. So therefore, in this kind of a representation, okay, of Kets and bras as column and row vectors, the inner product quite simply ends up becoming A star plus B star plus C star, just like a dot product. All right. So let's do this question. Consider two states, psi 1, which is written in a sort of a linear combination of other eigenkets, and psi 2, which is also written in a linear combination of other eigenkets, where phi 1, phi 2, phi 3 and phi 4 are orthonormal Kets. You remember orthonormality? You don't, right? So for example, okay, let me mention here, in a product, let's suppose, of a Ket with itself essentially represents the scalar product of the Ket with itself, and if it is equal to 1, we call it normalized. All right. And if we say that, okay, we have another Ket, phi and psi, if it is equal to 0, we say that they are orthogonal. Okay? So orthonormal means both phi and psi are individually normalized, but they themselves are orthogonal with respect to each other. That means there is no similarity between them. So then phi and psi are known as orthonormal Kets. So find the value of A. A is a scalar here, so that psi 1 and psi 2 are orthogonal. So to find out the orthogonality of these kinds of states, all you have to do is find out the scalar product. That's it, nothing else. So if you try to find out, let's suppose, psi 1 and psi 2, then you would write the bra of this psi1. The bra of this psi1 is what? Minus 2 iota. See, the moment I take the bra of a scalar, we have to write the complex conjugate of that particular scalar. And then we have the bra phi1 plus bra phi2 minus a star, because after all I'm taking the bra here, so a is a scalar. We need to take the complex conjugate of a star, phi3 and 4 phi4. Okay. If you want, you can take up your notebook and try to solve this question yourself. And then here we have psi2, which is 3 phi1 minus iota phi2 plus 5 phi3 minus phi4. Now, if we take a look at all individual products, because phi1, phi2, phi3, phi4, they are all orthonormal. That means if I take the product of phi1 and phi2, that would come out to be 0. Similarly, phi1, phi3, phi1, phi4, phi2, phi3, phi2, phi4, all those kinds of scalar products will come out to be 0 because they are orthogonal. But if I take phi1, phi1, that will come out to be 1 because it is normalized. That is the meaning of these Kets being orthonormal. That means they satisfy the property of normalization as well as orthogonality. So then only the individual products of phi1, phi2, phi2, phi1, phi1, phi2, phi2, phi3, phi3 and phi4, phi4 will survive. So that means 3 minus 6 I cap phi1, phi1 minus iota phi2, phi2 minus 5a star phi3, phi3 minus 4 phi4, phi4. Because they are normalized, this will be equal to 1, 1, 1 and 1. And this whole thing is equal to minus 6 I cap minus iota minus 5a star minus 4. But they are saying that we want to find out a so that the states given psi1 and psi2 are orthogonal. For them to be orthogonal, their inner product has to be equal to 0. That's it. So for this to be 0, minus 7i minus 5a star minus 4 is equal to 0, or 5a star is equal to 7i plus 4, or a is equal to, because a star, if I want to find a, I just have to take the complex conjugate of the right hand side. This is 4 minus 7i upon 5. This should be, made a quick mistake here, this should be minus here. So therefore this basically comes out to be 7i minus 4. Okay, so minus gets cancelled and I end up getting 7i minus 4. So this is the answer of A for the states psi1 and psi2 to be orthogonal. Alright, so if you're interested in these kinds of calculations and you're interested in learning about the numerical calculations of quantum mechanics, we have very dedicated courses that I take at Elevate classes. We have live batches, we have recorded batches targeting different examinations in the country. For example, Physics IIT JAM, CSI Net Physics, Gate Physics, TIFR and Jest Physics. I take live classes as well as provide recorded courses. And if you are one of those students who is preparing for these kinds of examinations, then you can check out our Elevate Classes platform. You can download the app. We have very latest batch which is starting in a couple of days for those students who are preparing for CSI Net and Gate Physics in the coming months. You can join if you are one of those students, or if you know somebody who is interested in these kinds of courses, if they're preparing for these examinations, then you can share this information with them. Keep in mind that the language is going to be English plus Hindi, because apart from me, there are other teachers also who are teaching in the platform. And this is only for students who are in India right now preparing for these examinations, okay? Because it's going to be a very structured preparation towards these examinations only. That is all from me today. I hope you have some idea regarding this kind of a Ket and bra representation. I will be taking this forward in the coming lectures. Thank you so much, guys. Have a nice evening. Take care. Bye-bye.